In this video, I'm going to be working Algebra 2 Homework 9.3, which is all about our log properties. So I think the first ones, we're just going to start not really with the properties, but just evaluating the logs. But I guess we could always look at these as going back to our fundamental identities. So, when we're trying to find the log with base 7 of 49, really what we're trying to do is trying to find the exponent we put on 7 to get 49. So what we could do is we could rewrite 49 as a power of 7. 49 is 7 to the 2, and then we know that the log with base b of b to the x is just going to be x. So the log with base 7 of 7 to the 2, that's 2. Then log base 3 of 81, okay, 3 to the 4 is equal to 81, so I'm going to write this as log base 3 of 3 to the 4, and that's going to be 4. Alright, see, maybe we can't just immediately think of what power of 4 we can write 8 as. So what we could do instead is we could say, alright, well, this thing is going to be, I'm saying to myself, what exponent do I put on 4 to get 8? And in order to solve this equation, we could just write both of these things as a power of 2. 4 to the x is 2 to the 2x. We've done that quite a bit. 8 is 2 to the 3. I feel like we've actually solved this equation a few times. 2x equals 3, x equals 3 halves. Okay, so log base 4 of 8 is equal to 1.5, or 3 divided by 2, however you want to write it. Log base 4 of 1 half, kind of same question, what exponent do I raise 4 to get 1 over 2? Okay, and maybe I'll just kind of work on that too. Okay, what is 2 to 4? It's the square root of 4. Okay, do that. And square root of 4, that's 4 to the 1 half. So I'm going to say, hold on, pardon me, 4 to the x, the square root of 4 in the denominator, that's 4 to the negative 1 half. So I can rewrite this. I say, okay, I'm taking log base 4. 0.5 is the same as 4 to the negative 1 half, and that's just going to be negative 1 half. Log base 2 of 32. Okay, 32 is a power of 2. That's 2 to the 5. Okay, so you could just say that's equal to 5, or you could rewrite this as log with base 2 of 2 to the 5th, and that's going to be 5. And since this is a homework all about log properties, I figured I'd make sure I was emphasizing all of these properties. Okay, but log base 32 of 2. Okay, so we've switched it. That's weird. Oh, yeah, and then there definitely have something to say about this one. So I'm saying, okay, what exponent do I put on 32 to get 2? Well, if 2 to the 5th is equal to 32, then that means that the 5th root of 32 is equal to 2. So I'm going to say 2 is equal to the 5th root of 32. And what exponent corresponds to the 5th root? This is going to be the 1/5 power. So I'm going to say that this is equal to 1 over 5. Okay, but alternatively, I'm going to get rid of this writing in red because there's something else I want to say here. Notice how log base 2 of 32 is equal to 5 over 1, but log base 32 of 2 is equal to 1 over 5. And what I would point out is, like, using the change of base formula, you could write both of these as a ratio of natural logs, and this would be natural log of 32 divided by natural log of 2 using the change of base formula, whereas this one would be natural log of 2 divided by natural log of 32. And I'm not saying that natural log of 2 is 1 and natural log of 32 is 5, but if you look at these, their relationship, it's a reciprocal relationship, so it shouldn't be surprising that I saw 5 over 1 and 1 over 5 for those two. Alright, now I've got a couple of these, and you saw these on the quiz last time, right? Something that we're going to just need to keep practicing, rewriting an exponential equation in log form and rewriting a log equation in exponential form. Okay, so remember, over here, the base of the exponential becomes the base of the log. Okay, the log is the exponent, so the log base r of something is going to equal k, and that thing will be equal to m. Okay, and then, let's see. Alright, so I'm going to approach this the same way. Log base d of k is going to equal z because the log is the exponent. But a person could, kind of getting you to start thinking about what we're going to do next time, a person could go and take the log with base d of both sides. And that would be, log base d of k. And a lot of people would tell you that's how you should think about this one, but I really want you to internalize the definition of a logarithm. That's why I always go back to base of the log is the base of the exponential, log is the exponent, that type of reasoning. What you could do is you say, okay, well, this thing on the left, log base d of d to the z, that's just equal to z, right? And then you'd have the exact same thing. If you just said, okay, on the left side I've got z equals log with base d of k. For the next two, we're doing the same thing, but in reverse. Okay, so the base of the log is going to be the base of the exponential. The log is the exponent. Okay, w to the h equals g. Okay, and then over here, the base of the log is equal to the base of the exponential. And c to the x is equal to p, because the log is the exponent. Now, over here on the right side, I figured I'd just do the same thing. Show you another way of approaching this. Take c to both sides power, right? So that would mean that c to the x is equal to c to the log base c of p. And this thing, okay, on the right, this is a different form of our fundamental identity, not one that we need to work with quite as much in Algebra 2, but we need to recognize that's just going to be the same as p. Okay, so then I would get p is equal to c to the x, however you want to look at it. Okay, now on the next page, I really like these problems. We're going to use the table of approximated logs to verify the identity. So we're just going to really see how this is working. So pretty much what I'm saying here is that natural log of 3 times 4 is natural log of 12, which is 2.5. On one hand, is natural log of 4 plus natural log of 3. So that's 1.4 plus 1.1. So we're even seeing the equality here in the tables that are, very approximate. Okay, log of 2 to the 3, natural log of 2 to the 3, that's natural log of 8, is equal to 3 times the natural log of 2. Okay, so that's what we're going to look at here. Okay, whoops, I meant to say, do this other side in red, 3 times the natural log of 2. All right, anyway, natural log of 8, we looked that up in the table, that's 2.1 versus 3 times 0.7. Okay, same thing. Natural log of 10 divided by 5, that's natural log of 2. On the other hand, I could look at this as natural log 10 minus natural log 5. Okay, so that would be 2.3 minus 1.6. And then, you look up natural log 2 in the table, that's 0.7. Okay, natural log of 3 squared times 2 is equal to 2 natural log 3 plus natural log 2. Okay, so that's using 2 properties. Okay, but 3 to the 2 is 9 times 2 is 18, so I've got natural log 18 on the left. And I've got 2 times natural log of 3, so 2 times 1.1, plus a natural log of 2, so plus 0.7. And that's 2.2 plus 7 is 2.9, which is what I'm seeing when I look up natural log of 18 in the table. And then lastly, okay, the change of base formula. So we've kind of got all of our properties appearing here. Is going to be log base 2 of 8 is equal to natural log of 8 divided by natural log of 2. Okay, log base 2 of 8, oh, okay, we know how to figure that out, right? On one hand, we could do it with the table, but on the other hand, we know, okay, what exponent do I raise 2 to get 8? I'm going to take 2 to the third to get 8, so I'm going to say, okay, this is 3. And then natural log 8 divided by natural log 2 is 2.1 divided by 0.7, and that's like 21 divided by 7, that's going to be 3. Okay, so we see it works. Okay, and then now we're going to use the table of common logs over here to estimate the values of these logarithms to 2 decimal places. Okay, so what we're going to have to do is write 500.6, 3 root 10, and 10 over 3 in terms of powers of 10 and the values of x we're seeing in the table. So like 500 right there, I'm going to use the 5 and then 100 because I know how to take log base 10 of 100. And notice that we're seeing all of these common logs, and so those are implied base 10. So I'm going to go over here and say, all right, so this is equal to the log with base 10 of 5 times 10 times 10. Now you could write this as 5 times 10 squared and then use that property also, but then maybe if you were thinking to do that, maybe you'll watch how I do it and you'll see that actually see why the property works. Okay, so this is going to be log base 10 of 5 plus log base 10 of 10 plus a third one, because we're just splitting over those multiplications. Those multiplications here become additions there. So log base 10 of 10. Okay, so I could combine those and make 2 log base 10 of 10s, right? And that would be what would happen if I just wrote that as 10 squared. Anyway, so that's going to be log base 10 of 5 is 0.70. Log base 10 of 10, what exponent do I put on 10 to get 10? That's going to be 1, plus log base 10 of 10, that's going to be another 1. So this is 2.70. Log of 0.6, okay, 0.6 is 6 over 10. So I'm going to say that this is log base 10 of 6 over 10. And, you know, that division, I can turn that into a subtraction of 2 logs. So log base 10 of 6 minus log base 10 of 10. Yeah. That's going to be equal to 0.78 minus, okay, what exponent do I put on 10 to get 10? That would be 1. Okay, if I had 78 cents and I subtracted $1, that would be negative 22 cents. Right? And that makes sense, okay, because the common log of 1 is equal to 0. Any log of 1 is 0. And so the log of a number that's less than 1 should be less than 0. Okay. Common log of 3 square root 10. Okay, so I'm going to split that up into the 3 and the square root of 10. So I'm going to say that's log with base 10 of 3 plus log base 10 of the square root of 10, which I'm just going to go ahead and write that as a power of 10 right now. Because I'm going to need that. Now I guess I need to look up log base 10 of 3. That was 0.48. So that's 0.48 plus the log base 10 of 10 to the half. Well, that's just going to be a half. So write that as a decimal number. And that's going to be 0.98. Log base 10 of 10 thirds, it's going to work very similarly to that one up there, B. It's just that the 10 is going to be first. So this will be log base 10 of 10 minus log base 10 of 3. Okay, we know that log base 10 of 10 is 1 because 1's the exponent I put on 10 to get 10. And then I look up log base 10 of 3, and that's going to be 0.48. So 1 minus 0.48, that'll be 0.52. Right, log base 4 of 10. Okay, so what I need to do is like, okay, I need to write this in terms of, I know what this is, and I know what, wait, no. Log base 10 of 4, I've got that in a table, right? So what I need to do is I need to use the change of base formula, because I don't have anything with log base 4. Okay, and 10 can't be written as a power of 4 or a power of 2 or anything that might be helpful. So I'm going to go over here and I'm going to say, all right, use the change of base formula. And that's going to equal log base 10 of 10 divided by log base 10 of 4. Remember, the change of base formula is probably the easiest to remember because this 10 is up higher than that 4, so it should be up higher, you know, when I write the change of base formula. And so again, log base 10 of 10, that's equal to 1. And this is 1 divided by log base 10 of 4. This better be, okay, yeah, 0.6. I was like, what am I doing? Accurate to 2 decimals? How am I supposed to do this? But this is actually one that we could do. Now, if you wanted to just leave it right here and say that's as accurate to 2 decimals as I'm going to be able to do on the second page of a homework, that's fine. Right? Totally fine. I'm not going to ask you to do this type of arithmetic on the test or anything, but I'm going to show you that 6/10, that's 3/5. And 1 over a fraction does just flip that fraction. So this is going to be 5/3. That would be 1.67. Okay? And let me just look that up real quick. Interesting. Actual value 1.66. So I think that's a pretty decent estimate there for just having a table and no technology. All right. So base 10 log of 4 over the 4th root of 10. Okay. So this is going to involve some maneuvering. Okay. So I'm going to split over that division right there. That 4 over the 4th root 10. So that'll be the log base 10 of 4 minus the log base 10 of the 4th root of 10. So I'm going to apply the property. And then I'm going to rewrite the 4th root of 10 as a power of 10. Okay, the 4th root is the 1/4 power. And let's say, all right, this is log base 10 of 4. What was that? 0.6. And then minus a 4th, which is 0.25, and that'll be equal to 0.35. All right, this next set of questions is like find the values of a and b that make the equation true. And while this is definitely solving log equations, we're not going to be solving this with like taking both sides to a power. What we're going to do is we're just going to try to collapse some expressions using log properties, or like maybe expand them using log, just use a log property to try to make one side look like the other. So I'm just going to zoom in and work one at a time. This one, okay, I've got a sum of 2 logs on the left, and I need to combine that to figure out what a and b are. So what I can do when I have 2 logs with the same base added to each other is I can multiply the arguments. So this will be log base 2 of 7 times 3. So that means that a is equal to 21 and b is equal to 2. For the next one, this is going to be the exact same. I've got a difference of 2 logs with the same base. So I'm going to go over there and I'm going to divide the arguments. So this is going to be log base 3 of 48 divided by 12. So that means that a is the argument of the log I end up getting. That would be 48 over 12 is 4. And b is the base. That's 3. All right. Okay. Now oh yeah, I know what we're supposed to do here. So we're just going to combine, difference of 2 of them. So this is log, I don't see any base on the left side, so that's implied to be 10. So that would be 8 divided by 5 times 35, right? The divided by because of the subtraction of the logs, and the multiplied because of the addition of the logs. Now, if you're like me, I don't know what 8/5 of 35 is, but if you think of it first as like 35 divided by 5, and that's 7, then multiply by 8, that's arithmetic I can do. So that's going to be log with base 10 of 56. Okay, so that means that a is equal to 56 and b is equal to 10. Okay, 5 natural log of 2 is equal to log base b of a. All right, so I have to get rid of that 5, and I think b is going to be e, right? This means base e log. So maybe I'll start there. Okay, but if I've got this multiplier out front, I can take that and I can swing it up as an exponent. Oh, whoops. And so I'm going to do that. And so I'm going to say this is the log with base e of 2 to the 5. Okay, so that means that a is equal to 2 to the 5th, which is 32, and b is just going to be that e number. Next, we've got log base 2 of 27 is a times log base b of 3. All right, so what we're going to have to do if we're trying to get this multiplier out front, it's because we've written something as an exponent, okay, on the inside of the log. So really what I got to do is I got to take that 27 and write that as a power of 3. But that's something I can do, right, because 27 is 3 to the 3rd. So I'm going to say that this is equal to log base 2 of 3 to the 3rd, which I can swing that exponent around the front, and that's 3 times the log base 2 of 3. So that means that a, being the multiplier, is 3, and b is going to be the base, that's 2. Right, over here, this is like a change of base situation. That's the only time we'll ever see two logs divided by each other, is when we're talking about change of base formula. So what I've done here is really what this needs to be is log with any base of 33 divided by log just with that same base of 7. Now up here I see no base here, so that means base 10. So I'm going to put that in here, and that means I need to have that down here. And so in the bottom I've got log base 10 of 7. That means a is 7 and b is 10. Right, again, two logs divided by one another, that has got to be change of base. So what's happening here is, okay, I've done change of base, so this is log base 2 of 16. Okay, because it's really whatever base you want. When you're doing change of base formula, the base of the result doesn't really matter unless you're trying to use like a scientific calculator to find a decimal value. Then you need to either use base 10 or base e, but you know, for the purposes of this problem, there's not really anything else going on. Okay, so I'm going to say, all right, this is b equals 2. I don't know what else to say. All right, natural log of the 6th root of x is a times the log base b of x. All right, so what I'm going to do is I'm going to rewrite the natural log as log with base e. The 6th root of x, I might write that as x to the 1/6 power. And then I can swing that exponent around the front. And then I've pretty much got it. Yeah, I've got a is equal to 1/6 and b is equal to e. All right, now number 7 is, okay, can I like collapse this down and write this as a single log? Okay. I forgot, some textbooks have a name for this, but I think the most clear instructions are just, hey, right, make this one log. Okay, so 3 log x plus log 3 plus 3 natural log y. I think that's a mistake. I don't know if is that possible? Let me think about that. Yeah, let's just make that a common log. And while I'm definitely not saying that it's impossible for us to write that previous expression as a single log, this is just Algebra 2. We're just familiarizing ourselves with logs right now for the first time, so we are not going to need to reach for like the hardest exponential and log problems on Earth for our purposes here this year. You know, maybe next year that's something we can investigate. But I'm going to say that this is common log of x cubed. Deal with that, you know, exponent property, plus the log with base 10 of 3 minus the log of y cubed. Just deal with all those coefficients first. Then I'll go to do multiplication and division, right, with that plus and that minus. So it'll be x to the 3 multiplied by 3 will be 3x cubed, and then I'll have to divide by y cubed, and that'll be the argument of my new log. Still the same base. You know, you can write a 10 there if you like. If you don't want to, you don't have to. All right, next one, I might go a little bit faster here. So this is going to be log base b. So you notice all log base b. And then the other ones, it's all natural log, or all log base 3. And so I really think that I just typed that wrong. So log base b of x squared to the 1/4 minus log base b of y squared plus log base b of 4. That's barely visible. There we go. All right, so I'm going to multiply the exponents in the first term. So x to the 2 times 1/4 is 2 over 4, so that'll be x to the 1/2. Pardon me. That's the log base b of y squared plus log base b of 4. Okay, and you know, if you want, you could write x to the 1/2 as square root x. We're going to multiply by 4 and then divide by y squared, and that's going to be the inside of my log. But you could also, I wouldn't care if you wrote it as x to the 1/2 power. You know, that's just as good. All right. Now see, half of the natural log of 9x that's natural log of the square root of 9x, because really what's going to happen is that's going to go up as a power of 9x, and it's the square root of all of 9x, right? Because I'm taking all of 9x to the 1/2 power when I apply that log property. Okay, so plus natural log of 3x taken to the 3 power, and then plus natural log of y squared. Squared would be y to the 4. Okay, so this is going to be the natural log of 3 square root x plus the natural log of 27x cubed plus the natural log of y to the 4. Okay, so I'm going to combine all those arguments with multiplication because I'm adding all these natural logs together. So I'll have a natural log of 3 times 27 is 81. Square root of x times x to the third. Square root of x is a 1/2 power. 1/2 power times the third power, that would be 3.5 powers. I might write that as x to the 7/2 and y to the 4. Now, if you felt like you were more simplified by writing square root of x, x cubed, or x cubed square root of x, be my guest. If you think that's more likely to get you credit in your class, that's how you should write it. Okay, but it's no more simplified one way than another. Over here, I'll write one more. Log base 3 of, okay, I'm bringing that 2/3 up as an exponent, because those coefficients multiplied in front become more powers. So this is x cubed taken to the 2/3 power minus log base 3 of 3/4 y to the 4th. Oh, that's tricky. Okay, so what they want you to do is they want you to try to do something with that 3/4 and the 4, but we're not going to do that because that's not one of our properties. That multiplier has to be out in front of the log. Has to be multiplied by the entire log, not just part of the argument. Okay. And probably in the big picture, the best way to write that would have been with some parentheses. But if there aren't parentheses, it's kind of got to be assumed the whole thing is the argument of the log, because there's nothing to indicate that this is like that, right? And no reason to believe that. Okay, so the next thing is, okay, nothing really to do here, log base 3 of 10. Right. But I will deal with that power of power scenario there, and I'll say, all right, that's going to be log with base 3 and argument x squared minus log base 3 of 3/4 y to the 4 minus log base 3 of 10. Yeah, sure. So when I'm subtracting two things, what's going to happen? It's definitely going to be division. So x squared over 3/4 y to the 4, but also over 10, right? Because I'm going to divide by 10 as well, which is like multiplying by 1/10, however you want to look at it. I think we're going to want to say, all right, that's 30 over 4. I think that can be simplified. 10 over 4 is the same as 5 divided by 2. So I've got 15y to the 4 in the denominator, and maybe that divided by 2 I'll kick back up to the numerator. Log base 3 of 2x squared over 15y to the 4. That was kind of a lot. But, that's log properties. All right, now we're going to write the expression in expanded form. And I think on a quiz or test, I would give you the instructions like, hey, write these expressions in terms of natural log x, natural log y, and natural log z. But, expanded form for homework, I think that'll be good enough. So I'm going to say, all right, first kind of deal with that multiplication and division, right? X times y squared divided by the square root of z. So that'll be natural log of x plus natural log of y squared minus the natural log of the square root of z, right? I'm going to deal with that multiplication and division on the inside of a log using an addition and subtraction of logs. So I can't do anything with natural log x, that y squared. I could, write that some number of natural log y's, and then I'll do the same with z, because the square root of z is the same as z to the 1/2 power. So in my opinion, expanding the log is actually a little bit easier than, writing them as a single log. Okay, over here, maybe I'll do this one in the opposite order. I'll deal with the fourth root first. So this will be common log of x to the 1/4 over y to the 3, which is going to be the common log of x to the 1/4 divided, or pardon me, minus common log of y cubed, and then I can swing the exponents down last. Okay, you can just do it like that. All right, let's keep moving. Oh, all right. Log base b of x squared y to the 1/5. Now, you could definitely write this as x to the 2/5, y to the 1/5, and then kind of split it up like that. But what I'm going to do is I'm going to kind of just go in the kind of the most natural order. So I'm kind of encountering this 1/5 on the outside. So I'll deal with that now. I'm just going to say that's 1/5 of the log with base b and argument x squared y. And so that'll be 1/5. Let's say log base b of x squared plus log base b of y. And then, okay, I'll probably bring that 2 down, that power of a power property. And I'll have 1/5 of 2 log base b of x plus a log base b of y. And, you could stop there, or you could call it 2/5 of the log base b of x plus 1/5 of the log base b of y. Maybe you'd be a little bit faster to have distributed that exponent at the beginning, but, it really doesn't matter. You're going to end up with the same thing, provided you take the right steps. All right, and the last one over here is log base 2 square root of y to the 4 over 4x squared. So you know what? I'm taking that square root first, and we're going to assume these variables are positive. Because we don't need to deal with any absolute values here. So I'm going to say that this is, I'll go up to the top line here, because log base 2 of the square root of y to the 4 would be y to the 2. The square root of 4x squared would be 2x. Yeah, that'll be good for us. So this will be log base 2 of y squared minus log base 2 of 2x. And maybe you think this, bringing down that y squared, that's as much as we're going to be able to do with this. But it's not. There's still more. Log base 2 of 2x can still be simplified, right? Because 2x is 2 times x, and that is something that I could split with multiplication. But because we've got that minus there, you seem to be very careful, right? Go back originally, the 2 and the x were both in the denominator, so they're both going to need to be somehow subtracted. So what I'm going to do is I'm going to say, all right, this log base 2 of 2x, I'm going to just work that in blue. So that's log base 2 of 2 plus log base 2 of x. And then I would need to distribute that negative over both of these things. But I know what log base 2 of 2 is, because 2 is 2 to the first. That'll just be equal to 1. So this is 2 log base 2 of y minus 1 minus a log base 2 of x. Alright, now this last set of problems, I really like these where you are trying to approximate a value of a log using some sort of properties and some given values. Really good way to test your knowledge of log properties. And it kind of gets back to what they were useful for, originally, before technology. But we're going to use the fact that we know the log of 2, 3, and 5 in this sum base. And we're going to estimate the logs to 2 decimal places. Oh, and I forgot about that. F is kind of like a bonus question if you're like, okay, dude, I get it with log properties, you can give me something else. That would be something for you to investigate. Log base b of 25, we need to figure out how to make 25 out of 2, 3, and 5. And so 25, first thing striking me is it's 5 times 5. Okay, or you could say 5 to the 2, doesn't really matter. So I'm going to say, all right, so that's equal to log with base b of 5 times 5, which is going to be 2 times the log base b of 5. Either way, if you're going to look at this as, adding the two logs together and then, combining like terms, or as an exponent, 5 times 5 is 5 to the 2. Doesn't really matter. So I'm over here, I am saying, oh wait, I need to look that up. 2 times 0.83 is 1.66. Okay. Log base b of 0.2, 0.2 is 1/5. So log base b of 1/5, might write that as log base b of 1 minus log base b of 5. Now if you wanted to call this 1/5 5 to the negative first power, it's going to be the exact same thing, because I can evaluate log of 1 with any base that's going to be 0, right? Because b to the 0 equals 1. So I've got the negative of the log of base b of 5, so that's negative 0.83. And log base b of 6, 6 is 2 times 3. Which I could compute by adding the logs of 2 and 3 in this base, and that would be 0.36 plus 0.56 would be 0.80, and 12 is 92. Okay. Log base b of square root of 2, what I'm going to do is I'm going to write that as a power of 2, swing that power around the front, and half of the log of 2 would be half of 0.36 is going to be 0.18. Okay, e is log base 2 of 5. Okay, I only have log base b, so what I need to do is I need to do a change of base formula. So I'm going to say that, whatever b is, we don't even know what it is yet, don't care. I'm going to say that that's equal to log base b of 5 divided by log base b of 2 using the change of base formula. And then that's going to be, what is that going to be? 0.83 divided by 0.36. I don't think that's going to be something I'm able to do. Okay, and 83, I don't know if that's divisible. I'm not saying it's not, but I don't see it if it is. So I'm just going to leave that there and be happy. And use a calculator to find b. All right, so what do I know for a fact? Log base b of 0.36 is equal to 2. Okay, so I could use any of these formulas and kind of like go back to the definition of a logarithm and use that to approximate the value of b. So on one hand, you could say, base of the log is the base exponential. B to the 0.36 is about equal to 2. You could say b to the 0.56 is approximately equal to 3. B to the 0.83 is approximately equal to 5. Let's see, you could probably, take the 5 to the 1 over 0.83, or 3 to the 1 over 0.56, or 2 to the 1 over 0.36. Figure that out. If you aren't able to figure out the value of b, maybe I'll just tell you what I think b is. All right, I did some investigation. I think b is approximately 7. Okay, so if you're not able to figure out why that's true, I think you should just come and talk to me about that before class next time, or contact me otherwise. But I think that'll be all for this video. Thanks for watching.